Dr. Wenlei Zhang and with Ryan Glasser, and he's going to talk about multimode entanglement in four-way mixing.
Hi everyone, thank you for giving me this opportunity to speak. So I'm a grad student at the Quantum Optics group at Tulane. So today I'll be talking about multimode entanglement using four-way mixing. So first, what is the motivation? So our goal is to build quantum networks that enable quantum communication between arbitrary network users. So to do that, we need to generate and distribute robust multimode entanglement, multipartite entanglement. So four-way mixing is a natural choice because we can generate, well, four-way mixing in hot atomic vapor. We can generate multispatial mode, and that is a good choice for distribution because they are separated spatially already, compared with, like, say, frequency modes. So people are already exploring different phase matching geometries using this process to generate multispatial mode entanglement. So today I will present one particular setup to generate tripartite entanglement. So first, this is the schematic for our standard four-way mixing. So a pump beam comes into a cell that's filled with, say, hot rubidium-85 atoms. And through a nonlinear process, two photons in the pump are annihilated, and then a pair of probe and conjugate photons are created. And this is the energy diagram for this nonlinear process. So this process involves four energy levels in the atom. And C is the phase matching condition for this process. So the phase matching is equivalent to momentum conservation. And so this phase matching condition is rotationally symmetric about the pump axis. So realistically, we'll have a cone of output photons, not just two lines that I've drawn here, but it's actually a cone. So what we can do is, let's consider this setup where we have two pump beams and we align the two pump beams such that the two output cones intersect at a single line. And that's this middle probe mode B here. So if we do that, in this process, so we can have two pump photons from pump 1 that are annihilated and create one photon in mode A and one photon in mode B. We can also have two pump photons from pump 2 that are annihilated to create one photon in mode B and one photon in mode C here. So the energy diagram is the same as the previous one, but the phase matching condition is a little bit more complicated and shown here. Right, so we have two from pump 2 and then two from pump 1, and creating probe photons and conjugate photons. So the Hamiltonian for this process looks like this. Here I've omitted the atom terms just for simplicity. That would be way too long if we include the atom terms. So the ABC operators are the mode operators for each mode. P1 and P2 are the mode operators for the pumps. And this part is the interaction part, where we couple two pump photons to mode A, B, or two pump photons to mode B and C. And the chi3-1 and chi3-2 are the third order nonlinearities for this nonlinear process. Right, so now we can use a bunch of approximations and stuff. So namely, we have to use the no pump depletion approximation and also the rotating wave approximation. And then we have to switch to the interaction picture, and we can obtain the squeezing operator. The squeezing operator is the unitary evolution of the interaction Hamiltonian. So it looks like this from the Hamiltonian that we had before. So we have the C1 and C2 here are the squeezing parameters, which I'll write out later on using R1 and theta 1 and R2 and theta 2. So one important thing to know is that this coupled, so what we're calling this is the coupled three-mode squeezing operator. This operator is not the product of two mode squeezing operators. So So this is similar to the situation where a two-mode squeezing operator cannot be factored into a product of two single-mode squeezing operators. And this is where the interesting stuff comes from. Right, so once we have the operator, the next part we want to do is we want to solve for the couple three-mode squeeze vacuum, and that is the output state of that operator acting on vacuum inputs. So this is what we want to obtain. So first, we want to see how the operator transforms the different modes. Then we can obtain these using the BCH formula. So all you have to know is that the mu's, the taus, the nus are functions of the squeezing parameters, R1, R2, theta 1, theta 2. And another important thing is the R here. The R is actually the square root of the sum of R1 squared plus R2 squared, and this is where the coupling comes from. So we have the Cauchy R term and the sinh R term. And right, the Z is just the ratio of R1 to R and R2 to R. Okay, so once we have this transformation of the modes, we can use the same method that we used to solve for the two-mode squeeze vacuum to solve for the couple three-mode squeeze vacuum. And the final answer looks like this. So the squeeze vacuum state looks like that, and the coefficients in front is that. So here we can see that mode B, the photon number in mode B, is always the sum of the photon number of A and C. And so in addition to the coupling term R, there's an extra binomial coefficient here that's n plus L, choose n, or choose L, the same thing. So this is also another term that shows the coupling between them, the two processes. So once we have the squeeze vacuum, we can calculate a bunch of all kinds of different properties. So the first thing is we want to look at the mean photon numbers and variances of each mode. So the M, just the mean and variance are defined in the standard way. So the mean of the photon numbers in each mode are listed here, and then the variances are listed here. So we can see that the variance of each mode is equal to the mean times 1 plus the mean. And this is a characteristic of a Bose-Einstein distribution. So each mode individually is a thermal state. This is the exact same thing as a two-mode squeeze vacuum. So here I've made some contour plots of the photon number, mean photon number, and the variance. So the variance grows faster than the mean, which is a thermal state. So, and also here we can see that the results for A and C are symmetric under interchange of R1 and R2, and for B itself is symmetric about the R1 equals R2 line. So the system is symmetric if we interchange R1, R2. Right, so next, this is a plot of the signal to noise ratio defined here for each mode. And in the strong squeezing limit, the signal to noise ratio goes to 0 dB. So this is all pretty similar to the two-mode squeeze vacuum, so no surprising here. So next we want to look at the intensity squeezing. So first, the definition of squeezing. So we will say an operator is squeezed if the variance of the operator is smaller than the standard noise limit, which I'm using subscript COH to denote the standard noise limit. The standard noise limit is just the variance of the same operator with respect to coherent states in each mode with the same respective mean photon number as the squeeze vacuum. So we can quantify the squeezing by taking the ratio of that, and then the standard noise limit can be calculated this way. So now we look at the number operator NB minus NA minus NC. So this operator experimentally corresponds to measuring the intensity of each mode and then taking the intensity of B and then subtract the intensity of A and C from the intensity of B. So for this operator, the mean is 0 and the variance is 0, but the standard noise limit is that, not 0. And we can see that this operator is always squeezed if R1, R2, and R both 0. This is the exact same thing as a two-mode squeeze vacuum where you take the intensity difference between the two modes. Here we have 3 modes, so we take the intensity difference between B and the sum of A and C. Right. Now, what we want to do, what we can't have in a two-mode squeeze vacuum is the intensity difference between pairs of modes. So this is something new with the 3-mode squeeze vacuum. So now we can look at the operators NB plus minus NA, NB plus minus NC, and NA plus minus NC. And the variances of these operators, 6 operators, are shown here. And the standard noise limit for the 6 operators are shown here. So here we can see that for these 4 operators, the variance is always greater than the standard noise limit, so they can never be squeezed. So what's interesting is that there is never squeezing between mode A and mode C, which at first we thought it was a little bit weird. So for the 2 operators that can be squeezed, NB minus NA and NB minus NC, here are some plots of the squeezing with respect to R1 and R2. So for NB minus NA, the region below the 0 line is the region where it is squeezed, and for NB minus NC, the region to the left of the 0 line is where it is squeezed. So here we have somewhat an unexpected result, because since R1 is the squeezing parameter between mode A and mode B, intuitively we would think that if we fix R2 and increase R1, we will see an increase in the squeezing of NB minus NA, right? But here we see the result is not that. It actually depends on the value of R2. So if we choose R2 to be fixed at 1.5 and change R1, there is no squeezing at all for NB minus NA. But if we fix R2 at 1 and we increase R1, first it's not squeezed, and then it becomes squeezed inside this region, and it becomes not squeezed again with large R1. So this is something that we did not expect, well, at least I didn't expect before I started this calculation. So this just shows that the intensity squeezing between pairs of modes is different from the 2-mode case. So next we want to look at the quadrature squeezing, but before doing that, we want to obtain the covariance matrix first. So the covariance matrix is just a matrix that contains all the information of covariances between the quadrature operators. So here, x1, p1 are the quadrature operators for mode A, and x2, p2 are for mode B, x3, p3 are for mode C. And the covariance matrix is just the second moment of this vector that contains all the quadrature operators. So this is what the covariance matrix looks like. And so on the diagonal terms, all the diagonal elements are just variances of each quadrature operator, and the off-diagonal terms are the covariances of pairs of quadrature operators. So here it's important to, so here it looks like theta 1, the covariance depends on the absolute value of theta 1 and theta 2, but we know that's not right, so because it should depend on relative phase instead of absolute value phase. Here, what theta 1 and theta 2 actually are is, this is the phase difference between the squeezing parameter C1 and C2 to the x quadrature of x, so to the x quadrature of each mode. So here, because I'm defining x as that, so I'm actually saying that the x quadrature is 0 phase reference for all the modes, for theta 1s and theta 2s. So experimentally, this means that if we were to use a homodyne measurement to measure the quadrature operators, then theta 1 will be the phase difference between pump 1 and the local oscillator used in the quadrature measurement, in the homodyne measurement. And then theta 2 will be the phase difference between pump 2 and the local oscillator. Right. So once we have this covariance matrix, then we can look at the quadrature squeezing. So now I'm looking at quadrature operators in this form, where the h's, h1, h2, and h3 are real numbers, and the u and v operators are just linear combinations of all the quadrature operators. So the variance of u and v can be written in terms of elements in the covariance matrix, and the standard noise limit is that. So you can make contour plots. So here is the contour plot of the squeezing of u and v for all three h's equal to 1 and a symmetric R1 and R2. So for u, it is squeezed at the four corners of this plane, and for v, it's squeezed in the center. So we can see here that there are regions of theta 1 and theta 2 where u and v are both not squeezed. So this is same thing that happens with the two-mode squeeze vacuum. And also that u and v cannot be squeezed at the same time. That is obvious because they don't commute. And for non-symmetric R1, R2, so here the only thing I've changed is the values of R1 and R2, keeping the sum the same, but changing it so that they are not equal to each other. So then the region where they are squeezed becomes different, and most importantly, if we choose theta 1 to be the right value, it will become squeezed regardless of theta 2. So for all of theta 2, it will be squeezed. So the next thing is we want to look at the actual entanglement, see if there is a tripartite entanglement or it's just pairwise entanglement, stuff like that. So first, we look at the entropy of entanglement between pairs of modes. So that's just the definition of the von Neumann entropy. So here I'm plotting so the y-axis is the von Neumann entropy of the composite of the composite system of pairs of modes minus the sum of the individual subsystems, of the entropies of the individual subsystems. So this difference, if this difference is smaller than 0, it means that A and C are entangled. And then, right, so same thing for AB and BC. And we can see that for all these values of R1 and R2, they are all smaller than 0. The 0 line is the line on top, and they're all negative. So this shows that each pair of modes are entangled. Right, so this shows exactly A and C are entangled, A and B are entangled, and B and C are entangled. Right, so, but the problem with the entropy is that it's not practical to measure entropy experimentally to show that they are entangled. So we need to find a criterion based on something that we can measure experimentally. So the best thing would be to use quadrature operators. So right before that, I need to talk about the definition of genuine tripartite entanglement and the distinction between full tripartite inseparability and genuine tripartite entanglement. So in some literature, they use these terms interchangeably, but that is not correct. These two terms mean different things. So full tripartite inseparability means that rho for a tripartite system, rho, cannot be written in any of these four forms. So the first three are biseparable forms, where you can separate the system into two parts, 1, 2 with 3 separate, and then 1 and 2 might be entangled in this case, then 1, 3. And the fourth case is the fully separable case. So if rho cannot be written in any of these forms, it's full tripartite inseparable. But genuine tripartite entanglement means that rho cannot be written as a convex sum of biseparable and fully separable states. So cannot be written as a convex sum of these three terms. So here we can see that for a pure state, these two are equivalent to each other. full tripartite inseparability means genuine tripartite entanglement for a pure state. But for a mixed state, what we can have is we can have a mixture of these three biseparable states. Then it is full tripartite inseparable, but not genuine tripartite entangled, right, for mixed state. Here, the results that I present are all for pure states. But if we want to implement this experimentally, we will definitely run into mixed states, and we need to make this distinction here. So the next is a criterion for characterizing genuine tripartite entanglement. So if we violate this inequality, this is sufficient to demonstrate genuine tripartite entanglement, where the U and V's are these operators here. So the difference between this and the previous quadrature operator is that this is two commuting operators here. So, right, so now this is the result of the product variance U times variance of V. And the variance of U and variance of V can be calculated using the covariance matrix again. So once we have that, it's a powerful tool to calculate any variance of quadrature operators. So here we can see that so A is for symmetric R1 and R2. So in the middle region is where the product becomes smaller than 1. So for phases theta 1, theta 2, if we choose the phases in the middle here, we can show that this state is genuine tripartite entangled. Oh, right. Remember, the criterion is only sufficient, but not necessary. And for not symmetric R1 and R2, we also have a region where this inequality is violated, and inside that region, we can demonstrate genuine tripartite entanglement. Okay. So, yeah, to summarize, here we've presented a dual pump setup for generation of multipartite entanglement using four-wave mixing in warm atomic vapor. And also we obtained the couple mode squeezing operator, couple three mode squeezing operator, and derived the squeeze vacuum in the Fock basis. And then we looked at the intensity squeezing and quadrature squeezing of this squeeze vacuum state, and we also showed that this state can be genuine tripartite entangled. And that's all I have. Thank you for your attention.
Questions?
Is there a discrete variable tripartite state that's analogous to the kind of tripartite state that you're making? I know for three-party we have GHZ and W, and those
right.
fall into different classes. Is yours like GHZ or? Like
Well, it's definitely so. If we want to look at genuine tripartite entanglement, then it's similar to GHZ, where it's actually genuine tripartite entanglement, right?
Yeah, I mean, if we take that n plus L and replace it with binary addition, then we would get, what would we get? I don't know, maybe that's not the way to think about it. Okay, but is it not clear which one it's like?
I haven't thought about it.
Okay.
Yeah.
But didn't you say yours is not completely entangled?
It is.
I
It
see.
is. If we look at the definition of full tripartite inseparability, just by looking at the entropy of entanglement, so here we see that rho AC. Well, I didn't write out what this is, but rho AC is equal to, the entropy of rho AC is equal to the entropy of rho B, and it's greater than 0. So the full tripartite density operator is a pure state, so the entropy is 0. But S of rho AC and S of rho B are both greater than 0, so that means the composite system AC and the system B are entangled. And same thing for AB and then C, and BC and then A. So according to this criteria, it cannot be written in any of these biseparable forms. and it definitely cannot be written in a full separable form. So then, according to this, it's a full tripartite inseparable state. And then for pure state, this is equivalent to genuine tripartite entanglement. So this state should be genuine tripartite entangled, just by looking at the entropy of entanglement. But using this inequality, this criteria for the quadrature operators is only sufficient, not necessary. So we can't go back the other direction. Yeah.
Just looking at that, I would assume those things wouldn't commute, and yet they do. Is there any like quick explanation as to why like, a whole bunch of x's and a whole bunch of p's in a weird combination?
The commutator of this is just equal to x2, the commutator of x2, p2 minus,
Yeah,
Oh.
it was root 2. so-
sorry.
Yeah.
I think I missed a 2 here. There should be a 2 here and then a 2 here. And then they commute. Sorry. Yeah. That's my mistake.
Yeah.
Oh.
There should be a 2 here and then a 2 here.
Omar?
Yeah, this is a general question, but typically second order nonlinearities are stronger than first order third order nonlinearities. If that's the case, then why people use four-way mixer to generate photon pairs?
Compared to like SPDC?
Yeah,
Or,
for example.
okay. Well, the bandwidth is a very big issue. So SPDC in nonlinear crystals, they are broadband. So the output photons you get for a typical like twin photon generation SPDC type 2 process, the output bandwidth of the signal and idler photon are like 50 nanometers, something like that. But here we can have very narrow bandwidth output photons. Like that's one reason. Like it's not that the bandwidth is completely different because for mixing atomic vapor, the D1 line is there's a dip in the D1 line, and then for nonlinear crystal it's broadband absorption.
Yeah, I think in part it's is it that you can do this in a vapor situation, not in a
Right.
crystal.
Right, that is different, and yeah, in a crystal it's broadband. So the output photon you get is the bandwidth is on the order of tenths of nanometers.
Well, there are techniques to
Right, yeah,
narrow it.
to make it narrower, but
But I see the point.
yeah. And here we have the important thing is we want multi-spatial modes. So if we were to doing a waveguide and stuff like that, you don't have spatial modes, but you end up with frequency modes.
And how bright your source is?
That's a good question.
Yeah, because you're using vapor, of course your intensity is
That
so much less.
I don't know because it will depend on like the squeezing mirror, the R1 here depends on a bunch of different things. It depends on the pump power, the duration of the interaction length of the time that atom sees the field, the interaction time of that, and it also depends on the nonlinearity here, the third order nonlinearity here, which it depends on the temperature of the system. So, yeah, that's another reason why. So the tunability in R1 and R2 are very limited. So that's why we want to look at quadrature operators where we can tune theta 1, theta 2 completely from 0 to 2 pi, and instead of tuning R1 and R2. Yeah.
Was there a question there? Yes.
Can you go to the entropy plots?
Yes.
So V was the center beam, right?
Yes, that's right.
Why are the features different between
Oh.
A and B and B and C?
This should be symmetric with that by interchanging R1 and R2, and they
Right.
are. Yeah, they are.
Okay.
So here, like, I'm plotting all against R1, so that's the reason why they're. If I plotted this against R2 and changed this R1, then they will be the same.
Okay.
Yeah, they are symmetric.
One more.
Yeah, so there's inequality that you violate that demonstrates tripartite entanglement. Seems
Yeah.
to depend very much on the fact that U is some combination of position measurements, I guess.
Yes.
And B is some combination of momentum measurements.
Right.
So how good do you feel about your measurements? Because if you're measuring not X, but something a little off from X, then this
Yeah.
isn't really like necessarily true anymore. So how confident do you feel, you know?
Yeah, exactly. This is the problem. Like, we need to set up 3 homodyne detectors, and also we have to make sure that they are exactly in phase with each other. The locals are exactly 0 phase. And that is the difficult part of why, that is the reason why this is only a theory and not
Uh-huh.
experiment. That is exactly the hard part, is to